Hello and welcome to the Drone Builders Collective. Whether you are tightening your very first bolt or fine-tuning a custom carbon fiber frame, you have found your crew. Before we dive into the hangar today, make sure to hit that like and subscribe button on whatever platform you are listening on. That way, you never miss a lesson in building the ultimate flight machine. This is the podcast where we break down the high-flying world of aerospace engineering into pieces you can actually use on your workbench. Every single week, we dive deep into the art and science of making things fly. We will explore aerodynamic principles, aircraft design, and robotic functions. You don't need a fancy degree to build something incredible. You just need the drive to learn, create, and launch.
Welcome to Aerodynamics and Flight Lesson 3, Wings and Lift, Stall and High Lift Devices. In the last lesson we learned how a wing creates lift, camber, thickness, angle of attack, pressure differences, and the turning of airflow all work together. But lift does not grow without limit. Push the angle of attack far enough, and something dramatic happens. The smooth airflow that was generating all that lift falls apart. That event is the stall, and understanding it is essential because most aviation accidents and small aircraft happen near a stall. This lesson explains what the stall really is, why it happens, how designers manage it, and how aircraft use movable surfaces called high-lift devices to fly safely and slowly for takeoff and landing. Why lift stops growing. The adverse pressure gradient. The trap that ends most arguments about lift is that it works beautifully right up until the moment it doesn't. So we need to understand exactly what goes wrong. Recall that pressure is low on the upper surface of the wing. When the airflow accelerates over the top, its pressure drops, but after passing the wing's thickest point, the air must funnel back toward the trailing edge, and to do that it has to slow down. Slowing means the pressure rises again. That rise is called an adverse pressure gradient because it pushes against the air's motion along the surface. Near the front of the wing the flow has plenty of energy to fight a rising pressure. Farther back, it doesn't. Now add a second piece, the boundary layer. Right at the wing's surface, air can't slide freely. The molecules at the very surface are stuck to the metal. Just above them, a thin layer of air is dragged along, moving slower than the free airflow far above the wing. That thin, slowed region is the boundary layer, and its speed matters enormously. When the surrounding airflow is accelerating, the boundary layer is energized. But the moment the boundary layer encounters an adverse pressure gradient with too little energy, the slow air near the surface simply stops. Worse, it can reverse and flow backward. When that backward moving air collides with the oncoming flow, the boundary layer is forced away from the surface. The smooth airflow detaches from the wing. This detachment is flow separation, and separation is the root of the stall. The wing is no longer smoothly steering air around itself. Instead, a large, churning region of turbulence forms over the trailing portion of the upper surface. Lift collapses not because the wing suddenly becomes incapable of generating force, but because the pressure field that created lift has broken down. The air no longer follows the wing, so the wing can no longer efficiently steer, and turn that air. What the stall feels like and what it does. A stall is not a discrete event that happens at one perfect airspeed. It is a progressive breakdown that begins at the back of the wing and marches forward as angle of attack increases. At low angles of attack, the flow is attached everywhere and lift grows smoothly. As angle increases, the adverse pressure gradient gets steeper, and separation begins near the trailing edge. Lift keeps growing. The separated region at the rear is still small, but you can sense trouble. The airflow is beginning to let go. As the angle increases more, the separation point moves forward, the turbulence broadens, and lift reaches its maximum. That peak is called the maximum lift coefficient. The angle of attack at which it occurs is the stall angle. Beyond that, lift actually decreases as angle of attack increases further, and drag rises sharply. The companion of the stall is buffet, an unsteady vibration you can feel in the controls and airframe as the separated flow slaps against the structure. On a well-behaved aircraft, buffet arrives as a warning. The nose pitches down on its own, and the aircraft naturally unloads the wing. On a poorly designed or mistrimmed aircraft, the stall can lead to a spin or loss of control, especially if one wing stalls before the other. Here is the crucial fact about stall speed. An aircraft stalls at whatever airspeed corresponds to its current configuration, weight, and density conditions, not at a single painted number. The wing stalls when it reaches the stall angle of attack. Because the stall is governed by angle of attack, you can stall at almost any speed, including a speed well above the published stall speed, if you pull hard enough. This is called an accelerated stall. If you yank back on the stick in a level turn, load factor rises, the wing must produce far more lift, and it reaches its maximum lift angle at a higher speed. The aircraft can stall while flying fast. Pilots are trained to recognize pitch, buffet, stall warning horn, and airspeed to avoid the stall and to recover by lowering the nose, adding power, and reducing angle of attack. Stall speed, weight, and wing loading. The stall speed is a useful operational number because pilots plan around it. Lift must equal weight in steady, level flight. The heavier the aircraft or the lower the air density, the higher the airspeed at which the wing reaches its maximum lift. The less wing area, the higher the stall speed too, because each unit of wing must carry more weight. The connection between weight and wing area is called wing loading, the aircraft's weight divided by its wing area. A fully loaded airliner has high wing loading and a relatively high stall speed. A light trainer has low wing loading and a low, forgiving stall speed. Every pound of extra weight fuel, payload, or ice raises the stall speed and reduces the safety margin in slow flight. How designers manage stall. Aero twist and washout. A stall is dangerous in practice when it is asymmetric, one wing stalling, while the other still produces lift. That sets up a violent roll and can precipitate a spin. So a major goal in wing design is to make the stall occur first at the wing root, near the fuselage, where the ailerons at the tips are still effective and where the rolling moment is least destructive. The main tool is washout, also called aerodynamic twist. The wing is built so the root is set at a higher angle of attack than the tip. When the root reaches its stall angle first, it separates and stalls well before the outer wing does. The wingtips, which carry the ailerons, stay attached and keep working. The aircraft pitches down predictably instead of snapping into an uncommanded roll. Washout, combined with geometry that sizes the tip chord so the tip doesn't stall first, is how a well-behaved wing provides a progressive, controllable stall. Surface contamination changes everything. Wing behavior depends on the surface being clean. Ice, frost, snow, dirt, bugs, or even a rough patch can change stall behavior dramatically. Contamination destroys the smooth boundary layer, causing early separation at angles much lower than the clean wing stall angle. Ice changes the airfoil shape. Dirt and bugs roughen the rear surface. Both shorten the effective aerodynamic performance and raise stall speed and drag. This is why aircraft are de-iced before flight and why pilots check for ice, frost, and contamination not just for cosmetics but for safety. A contaminated wing can stall at a lower angle and a higher airspeed than the pilot expects, which is especially serious on approach and takeoff. High-lift devices. The reason planes can fly slowly. There is a genuine design conflict lurking here. Efficient high-speed cruise favors a clean, relatively thin, modest camber wing that produces lift efficiently at low angle of attack. But there will always be moments when an aircraft needs to fly slowly and create enormous lift. Takeoff and landing. A wing designed purely for cruise would need a dangerously high, near stall angle of attack and an absurdly long runway to reach enough speed. The engineering answer is to make the wing's shape changeable. High-lift devices extend the effective camber and area at low speed, then retract them for cruise. The two big families are flaps and leading-edge devices. Flaps, changing camber and area. Flaps are hinged or sliding surfaces on the trailing edge. When deployed, they do two main things. They increase effective camber, letting the wing produce more lift at the same angle of attack. Some designs also increase wing area by extending backward. This extra lift lets the aircraft fly more slowly without reaching the stall angle, so a landing approach can be slow enough to give the pilot reaction time and to shorten the runway, while the wing still produces enough lift to carry the aircraft's weight. But flaps are not free. They add a great deal of drag, sometimes deliberately. On approach, this drag is useful. It enables a steeper, more stabilized descent without gaining speed, and it helps the engines respond quickly if the pilot needs thrust, because the engines are already at a moderate setting. On takeoff, pilots use a smaller flap setting, enough extra lift to shorten the ground roll, but not so much that climb performance suffers from added drag. There are several flap types. Plain flaps simply hinge down. Split flaps deflect a panel from the underside only. Slotted flaps leave a gap between the flap and the wing, allowing high-energy air to blow across the top surface and delay separation, giving more lift for a given deflection. Fowler flaps slide backward and down, increasing both area and camber. The most effective type. Slats and slots, saving the leading edge. The enemy of high lift is separation on the upper surface, which often starts near the leading edge at high angles of attack. Flaps help the trailing edge but don't protect the front. Slats and slots address the nose. A slat is a small airfoil ahead of the main wing's leading edge. When deployed, it opens a slot gap between the slat and the wing. High-energy air is forced through this slot and blown over the upper surface. This energizes the boundary layer, helping it stay attached to much higher angles of attack. The result is a dramatic increase in the maximum lift the wing can produce, and an increase in the stall angle. Slats let an aircraft fly slower and steeper than flaps alone would allow. They also change the effective camber of the wing. On many airliners, slats coexist with flaps. Flaps handle the trailing edge lift. Slats protect the leading edge so the flow stays attached. Together they produce the large, slow, high lift condition needed for a gentle landing. Spoilers add drag and kill lift. A spoiler is a flat, hinged panel on the upper surface that, when raised, deliberately destroys smooth flow. It kills lift and adds drag. Spoilers serve several purposes. As flight spoilers, they dump lift and help the aircraft descend or land firmly. As ground spoilers, they strongly reduce wing lift after touchdown so the wheels bite harder into the ground and braking becomes more effective. Some aircraft use spoilers differentially as spoilerons to assist rolling roll control while also producing drag. Spoilers are the opposite philosophy of flaps. Flaps add lift, spoilers kill it. Both are essential tools in the pilot's hands. Putting it together, a landing approach. Let's pull all this into one mental picture. An airliner lining up for a landing. On final approach, the pilots select full flaps and, if fitted, slats. The wings camber and area grow, producing huge lift at a modest airspeed. The aircraft flies slowly, which gives the pilots time and keeps the landing distance short. The high drag from the deployed flaps lets the wing descend on a steeper glide path without accelerating. The pilot manages angle of attack so the wing produces exactly the right amount of lift to track the glide path, neither ballooning up nor sinking too fast. If the slow flight is done carelessly, the pilot adds too much angle of attack, the flow separates, and the wing stalls. The horizontal tail is designed to keep the nose pitched down so the aircraft responds, but the pilot must unload the wing, lower the nose, add power, and let the air reattach before attempting the landing again. Just before touchdown, the pilot rounds out, raising the nose slightly to reduce the rate of descent. This is a careful dance near the stall, which is why the approach is flown fast enough to keep a safe margin above stall speed. On the runway, the pilots deploy ground spoilers, lifting the spoilers to kill the lift, so the aircraft settles onto the runway and the brakes work. The landing is complete. High lift devices are the reason a heavy airliner can land on a runway instead of needing a football field 10 miles long. Key takeaways. The stall happens when the boundary layer separates from the wing due to an adverse pressure gradient, breaking the pressure field that created lift. Lift grows with angle of attack only up to a maximum. Beyond that, lift falls and drag rises. Because the stall is caused by angle of attack, an aircraft can stall at any speed if you pull hard enough an accelerated stall. Stall speed rises with weight, decreases with wing area, and increases in thin air. Washout ranges for the wing route to stall first, keeping the ailerons effective and producing a predictable nose down instead of a roll. Surface contamination: ice, frost, dirt, bugs, early separation, raising stall speed and changing stall behavior. Flaps add effective camber and sometimes area, giving extra lift with extra drag at low speed. Slats and slots energize the boundary layer at the leading edge, increasing maximum lift and the stall angle. Spoilers deliberately destroy lift and add drag, aiding descent, ground braking, and roll control. High lift devices let a heavy, efficient cruise wing become a slow, high lift wing for takeoff and landing. Next, 1.4 Drag and aerodynamic efficiency looks at all the ways air resists an aircraft's motion and why designing for low drag and the right kind of drag is central to making an aircraft efficient.
And that brings us to the end of this episode of the Drone Builders Collective. Thank you so much for hanging out and building with us today. If you enjoyed this episode, please take a quick second to like, subscribe, and leave us a review on your favorite podcast app. Your reviews help other builders find our hangar and join the crew. Don't let the conversation stop here. Leave a comment on your favorite app or send us an email with suggestions for future episodes. Keep your batteries charged, your props balanced, and your mind curious. Until next time, clear skies and happy building.